But today's webinar is GHGSat, and very, very much looking forward to your webinar today, Jean-Francois. Without further ado, I'll turn it over to you.
All right. Thank you very much. I appreciate the opportunity here. And to make sure I calibrate things properly, how long do these typically run for, so that we can have time for discussion as well?
20 to 30 minutes, with anywhere from 10 to 30 minutes of questions. Okay,
that's plenty of time. That's perfect. So thank you again for the introduction here, and I'll get things started. So thanks everyone. So GHGSat pioneered the measurement of methane directly from industrial facilities using satellites. And we did this with our first satellite in 2016. And it is actually still true today. We're still the only entity in the world with a satellite specifically designed for that. And I say entity because it includes as well space agencies around the world. So not even NASA or the European Space Agency have the capability that we have with our satellites. So what makes us so different is, among other things, the spatial resolution. So we make our measurements at 25-meter resolution, and you'll see in the next slides how different that is compared to satellites that have been monitoring greenhouse gases for decades, but they've been doing it at a regional or global level. So with the lessons learned from this first satellite that we had launched in 2016, we built all those lessons into the next two satellites that we were aiming to launch, and actually the second one just launched in September. The third one is ready to go right now. It's actually launching in less than a month on January 14th on a SpaceX rocket. And these two satellites were designed to provide an order of magnitude, so 10 times improvement in performance over the performance of the first satellite. And in the next few slides, I'll be showing you some of the early results from that, because the results have been really impressive and exciting for our team. So looking a little bit to the future here, we are also planning to launch 3 more next year in 2021, so 3 more satellites, and then 5 more by the end of 2022, which will then take us to a constellation of 10 active satellites by the end of 2022. And also a quick note on the aircraft instrument that we designed that is based on the same sensor that we have on the satellite. So that started flying in December of last year, so a year ago, and I'll also be presenting some results from that instrument, because the compatibility between the two systems is very interesting, but it also highlights the compatibility of our satellite data with any other system for that matter. So the theme of collaboration, it will be a recurring one here. This is something that's very important to us at GHGSat, and there's wide acknowledgement within the industry that there's no single solution to address all emissions. You really need a combination of different technologies and systems to do that. Now, to give you some of you might know already about us, but so this will serve as a reminder, but to give a very quick overview as to what our capabilities are about. So first of all, it's a spectrometer instrument we have on the satellite, but it's not the typical type of spectrometer that you might be accustomed to seeing on instruments usually. So it's not a vertical grading. It is called a Fabry-Perot spectrometer. So it is instead a ring spectrometer. So the range of frequencies is covered through concentric rings within a lens. So every ring represents a different frequency in the range of interest. We perform our measurements at 25-meter resolution, as I mentioned earlier, and we do not constantly acquire data. So that's a very important thing to understand. Some satellites acquire data constantly as they sweep the surface of the Earth. We do not do that. We take imagery in 12 by 12 kilometer images, and the reason why we do that is to really focus on the facilities. So these other satellites look at what's called absolute column concentration. So they're looking at more regional concentrations. We are focused on facilities. On the left here, you can see an example of one of our images in terms of the field of view in red, the 12 by 12 kilometer image. And here you're looking at three quite large LNG terminals in Australia that are adjacent to one another. So this highlights not only our ability to monitor multiple sites at a time. So here it's three terminals, but of course, when you're looking at an area like the Permian in Texas or the Eagle Ford, you're looking at dozens and sometimes hundreds of sites at the same time that we can measure. But also for a large facility like an LNG terminal like this, the image on the right highlights how our results can help pinpoint where in the facility the leak is coming from. So that you can see a 25 meter by 25 meter grid overlaid on top of that facility. And of course, we're not able to say which leak or which valve or which flange is leaking, but we are, however, able to direct facility. Okay, this is where we've observed the leak, so that the personnel on the ground can be directed much more effectively and with more focus, instead of constantly surveying the whole facility with methods on the ground without knowing where leaks may be. Each satellite takes about 2 weeks to come back to the same spot on Earth. So as we add more satellites, the revisit time, the number of opportunities gets shorter and shorter. So with three satellites, we are looking at 5 to 6 day revisit, and eventually with 10 or more, then the possibility of having daily revisits becomes a possibility at certain sites. So I mentioned the technology a little bit in the previous slide, so I won't dwell on this for a very long time, but if there are questions, I'll be happy to field them. But again, we're looking at the absorption of light by methane, which we then translate into a measurement of concentration. So on the graph at the bottom of the slide here, you can see the absorption line of methane across the spectrum of interest, so 1600 to 1700 nanometer, and the blue line represents that absorption spectrum, and you can see the features that are highlighted by the dotted lines represents areas that are very, very typical to methane. So it's almost like a fingerprint. So it's unique to methane, and this means that if we see absorption along those lines, then we know that we're seeing methane. So we can make the retrieval, make the calculation to convert that absorption to a measure of concentration. So I've mentioned that other satellites are looking at they've been looking at greenhouse gases for a long time. Tropomi this chart is one of them. It's probably the state of the art in the scientific world right now, along with GHGSat from Japan. But this is a European satellite. It is an instrument on the Sentinel-5P satellite. But there's many other satellites that have been looking at greenhouse gases. But the point here that I want to make with this particular slide is that when looking at measuring methane from space with satellites, there are two factors that are really, really crucial, and they need to be considered together. It can't just be one or the other. The first one is resolution. So I've been talking a lot about the fact that we make our measurements at 25 meters. This is what separates us. But now you can start seeing why. Tropomi measures at 7-kilometer resolution, which, of course, if you're trying to examine a facility and a single pixel that's 7 kilometers by 7 kilometers, you can imagine it becomes very difficult or essentially impossible to detect who's responsible for those emissions. So so you'll see in the next slide actually a comparison between results from Tropomi and what we do. You'll see how it's different, but you also get some appreciation for how compatible those systems are. So, so the second aspect that's really crucial here is the detection threshold. So it can't just be about resolution. It also has to be about detection threshold. And even though Tropomi is designed to look at regional concentrations, the estimated detection threshold for a facility would be around 4,000 kilograms per hour. So you're looking at 4 tons per hour approximately. This would be a massive, a very, very big leak. So operationally, that would not be really useful for any type of company or operator. In contrast, our first satellite was at 1,000 kilograms per hour, but we knew that it was not performing to its full capability. That's why we took the lessons learned from that and incorporated them into our next 2 satellites, which were designed to be at a detection threshold of 100 kilograms per hour in moderate wind conditions. And in very calm weather, we're expecting to be able to go as low as 35 kilograms per hour. And you'll see in the next few slides here that we're already approaching this detection limit, which really makes it possible for us to see a lot more leaks. Now, if you haven't seen what our results look like, here are 2 examples of what we do, and there's a few things here to highlight. So first, we overlay our imagery, our results on high-resolution imagery from other satellites. So in this case, imagery that might have been taken from Google Maps or from other sources of high-resolution imagery. And the reason we do this is because at 25 meters, we can see some of the features in the image, but we can't clearly see the facilities like we do here. So on the left, you have a coal mine in China. These are the surface operations of that underground coal mine, and the methane is vented through a large fan at the surface, and we see these types of plumes all over the world, and we've measured them in China, Mongolia, Australia, the U.S. So underground coal mines are very well known and very large sources of methane. So we measure them on a weekly basis. On the right, a bit closer to the obviously the oil and gas industry here, you have an example in the Permian in Texas, and this is relevant for 2 reasons. First, you can see that this particular plume of methane is associated with this facility very precisely. Now, we're not able to identify which of these tanks in the tank battery is responsible for that leak, but we are, however, able to pinpoint this particular facility. And the second reason why it's relevant is because in a region like this, as you know, there could be dozens or hundreds of different sites, well pads, compressor stations, miles of gathering pipes around as well, and these are all potential sources of leaks. So we're able to monitor all of these at the same time in the same image, and if many of them are leaking at the same time, then we can start differentiating. And of course, if there's a flare on site, and that was one of the early questions that was mentioned, we would be able to identify if a flare is extinguished. We've measured dozens of these around the world. If a flare is malfunctioning and not combusting properly, that is a different proposition. And this is something that we're very keen to study more with our new the satellite that we just launched in September. Because if a flare is only burning at, let's say, 90% efficiency, it sounds like it wouldn't be enough methane to detect from space. But some of these flares are in fact very large, so 10% might still equate to several hundreds of kilograms per hour. So that's certainly something that we're keen to investigate more. And in fact, we've seen some early results with our aircraft instrument where we can see the flare is still lit, because that appears as a white dot in the infrared imagery. So we know the flare is still lit, but we see methane around it as well. So the possibility, the capability of the technology to do it seems to already be there. Now it becomes a function of determining if the detection threshold of the satellite would be sufficient to detect that at multiple flares around the world. So this particular this is a clip that I will be starting in a second, but what I want to put into context before I started here is what you're about to see. So on the left, you'll see results that we've been measuring over the last 2 years in the region of Central Asia, and you'll see multiple leaks appearing and disappearing in this image. It's a very, let's call it prolific region of the world for methane leaks. And these are all oil and gas installations. So they can be unlit flares, they can be compressor stations. We also have processing plants in there. We have gathering pipes and extraction sites. So a very wide array of oil and gas facilities here, each leaking at different times over the last 2 years. And on the right, you'll see the tropomi imagery that was acquired on the same day. Now you'll see that on some of those days there's no data available, and that's because, again, at 7-kilometer resolution, if you have any clouds in a single pixel, in a 7-kilometer pixel, the whole pixel is lost. So for us at 25-meter resolution, we can see in between clouds and still get results. So I'll start this short clip here, and what you'll start seeing is as you see leaks on the left, on the right you see an overall color enhancement over the region, which tells you there is methane present, but identification of the facility is simply not possible. Now, this is not a comparison that's made to show how much better we are than this system, because obviously they were designed for different reasons. But it primarily highlights how useful the data on the right is for us in identifying where to point our satellite in the world. So we see these enhancements, we know there's the presence of methane in that region, and then we can direct our satellites over there and figure out exactly which facility is responsible, and then start monitoring on a regular basis. So this type of collaboration is really crucial to us, as I mentioned at the onset. And this is something we use on a daily basis now as part of our own analytics service, and I'll have a bit more on that in a second. So this collaboration with Sentinel-5P and Tropomi is very near and dear to us, again, because we believe in the power of how different systems augment each other. So we've been accepted as part of the European Space Agency EarthNet third-party mission program to evaluate our data and eventually be included into EarthNet. We've also made 5% of the capacity of this satellite available to scientists through a program with the European and Canadian space agencies. So we're also committed to improving the overall knowledge and understanding of methane emissions with our own data. So I mentioned our second satellite that we launched on September 2nd. So within 2 weeks of that launch, actually less than 2 weeks, on September 15th, we were already doing testing with it. And this particular test here is what we call a controlled release test. And it's a test where we release a known quantity of methane that's accurately measured on the ground. And as we overfly, we make the measurement at the same time and then compare the results. So in this particular case, this test was done at 264 kilograms per hour. So at that time, that was 5 times better already within 2 weeks of the launch. It was 5 times better than our first satellite. Now, anecdotally, this was also at that time the smallest methane emission ever detected from space. I say anecdotally because since then we've been breaking that record almost on a weekly basis. So we've now gotten closer and closer to the 100 kilograms per hour objective that I mentioned in the first few slides. So in an operational setting, we've seen leaks that are much smaller than this. And also to speak to the accuracy of the measurements, we've done other controlled release tests, one of them with one of the members of OGCI. And we've this was a blind release. This was a blind test, so we had no idea of the location of the leak, nor did we know the size, the magnitude of that leak. So first, we were able to pinpoint exactly where the leak was, where the emission was released from. But more importantly, the release rate on the ground was 234 kilograms per hour, and our measurement came in at 226 kilograms per hour. So our measurement was very, very close, actually, closer than anyone could expect for this type of technology. It's completely normal to assume some error rate, error percentage within the results. So this was a very encouraging test. Of course, we have many more of these that are planned in order to continue fully characterizing the performance of that instrument. Now, before I leave this slide, I just want to draw your attention to the two measurements, the two bookend measurements that were performed with our aircraft. So these were performed 2 minutes before and 2 minutes after. And I say our aircraft, it's really our instrument on an aircraft, because the instrument is designed to fly on any aircraft. But the idea here was to first confirm that the leak was continuous throughout the duration of the test, but also it allows us to do cross-validation between the two instruments as we get data at a much higher resolution. So the aircraft operates at less than 1 meter resolution, and also has a much finer, a much lower detection threshold. So you can see the definition of that plume is much more pronounced, much better, much more precise. Now, to that end, to compare a bit further the performance of our first satellite versus what we're seeing today with our new satellite, this is over the same area of Central Asia I mentioned earlier, where we see leaks on a regular basis. And these two measurements were taken within a day or so of each other. Now, on the right, you see what our first satellite, Claire, could see. So this is a well-known leak that's been leaking continuously for a long time. And on the left, you see the same leak with our new satellite, Iris. But you can see a lot better definition around that top leak. So you can see the distribution downwind because the detection threshold is much lower. So we're able to really see the definition of the plume. But more importantly, you see these 4 other smaller leaks below, which before, with our first satellite, were completely invisible to us, so to speak. So this really serves to highlight, and of course the black background helps here in order to make these leaks pop. So we overlaid it over a black background instead of high resolution imagery here. But this really serves to illustrate that the power of the new capability here, and seeing more and more of these leaks, and to provide data that's increasingly useful to operators and to companies working with oil and gas satellites, to oil and gas companies trying to use satellites to start better understanding their emissions. Now, a quick note here on other systems, other satellite systems, and really how that capabilities is different, but also very compatible. So tropomi is one type of instrument. It's a spectrometer much like ours, but there's also a class of other instruments called hyperspectral or multispectral satellites, which also have the ability to see leaks, to see methane. They, in some cases, they have a higher resolution than tropomi. However, their capability to see smaller leaks is essentially non-existent. So they can only see these very, very large leaks once again. So you remember I talked about first resolution and then detection threshold. So really, again, this highlights the importance of having those two, because yes, you can see massive leaks, massive blowouts. You might have heard of the Belmont Belmont leak in Ohio a few years ago. So this was very highly publicized. Of course, everyone was aware because it was a very big, massive event. Similarly to Aliso Canyon, the picture below. So these are the types of events you can see with these instruments. Like comparatively, what we aim to see with our instruments at GHGSat, it's more the fugitive emissions from oil and gas facilities. Like for example, a thief hatch that's left open. For example, an unlit flare that you can see at the bottom left, or a liquid unloading event. So instead of seeing just 150 or 200 massive leaks a year, it opens up the possibility to see tens of thousands of leaks per year as our capacity increases with more and more satellites worldwide. So to kind of bring that point home here and show, kind of display that compatibility in a different way, this particular curve might be something that many of you are familiar with. This is from the Brandt study from Stanford University. This was a meta study that looked at 18 different separate studies that over the whole lot looked at almost 12,000 sources of emissions in oil and gas in the US. And what this study famously concluded is that the majority of the volume of methane that's emitted comes from a small number of leaks. So in other words, there's a number of really large leaks, and finding those leaks fast can help you address the majority of the issue very quickly, which then allows you to focus your efforts on the remainder and kind of close the loop. So you can see at the bottom these hyperspectral, multispectral satellites and tropomi. They can find the biggest of the biggest leaks. So really, there's so few of those that it only adds up to about 5% of the total volume emitted. So while it's interesting information, operationally, it's not very useful. What we're doing now with our new satellite, starting with Iris and then Hugo that we're launching in January, and with the rest of the constellation, at that current detection threshold, we can address up to 70% of the methane that's emitted. So basically, by doing frequent satellite monitoring, 70% of the problem can be addressed right away. And that can be done affordably because satellite monitoring doesn't require the deployment of anyone on the ground. So it results in a lot of savings cost. Different technologies. So here I have the GHGSat aircraft sensor here to show coverage for the next 20%, but it could be drones, it could be fixed systems, it could be optical gas imaging cameras. All these systems make it possible to detect smaller leaks that can't be seen with the satellites, but in turn, they're also typically more costly. So it allows you to use these systems more judiciously, with more focus, in order to kind of, again, close the loop and find as many leaks as possible at the lowest possible cost. And in the end, it leaves you with less than 10%, usually 5 to 8% of the leaks. Now, this is a really, really high number of tiny leaks. So you're looking at the flanges that are not bolted properly, the valves that are leaking very slightly. So instead of chasing these thousands of tiny leaks that really represent a small portion of the total of methane, you can focus on the big problem first, and then deploy resources more selectively to address these smaller leaks, instead of constantly trying to look at everything at the same time with, for example, optical gas imaging cameras. So I'm coming near the end here, but one very important note I need to make is this commitment that we've made in the last 2 years to really develop our capabilities on analytics. So I've made a point also of mentioning this idea of collaboration and using all the data that's available. Well, this is not by coincidence, because we ingest terabytes of data weekly. From other satellites, other sources of information, including databases like the Texas Railroad Commission information, information on incident reports. And so we incorporate all of that, and now we start performing analytics using AI and machine learning. So within our platform, within our portal, which is based in Esri, which many of you would know, we would show a customer's sites on the map like you see right now, but then we start providing different layers of information that start informing on the state of methane first regionally, and then kind of getting closer and closer to the facility level as needed by that particular operator or customer. So here you can see the methane concentration on a 2 kilometer by 2 kilometer resolution. And we also provide what we call hotspot detection. So the exclamation marks that you see here would be highlighting areas where, yes, like the concentration is higher, but it's also higher than it is historically. So for example, there might be areas that have a high concentration, but maybe it's always higher because there's a swamp there, or maybe there's a rice paddy, which causes the atmospheric methane to be constantly high. In these cases, and when you see a hotspot, it could be an indication that an event took place recently if the concentration has been higher. We also, and again, flaring was mentioned at the onset, but there are satellites that provide us with details of flaring worldwide. So throughout the Permian, throughout the Eagle Ford, and all over the world for that matter. So we know where the flares are. We can monitor whether or not they're lit, and we look for trends and patterns. And if flares suddenly turn off after being on for a long period of time, it might be perfectly normal. It might be because maybe production ramped down at that site, but it could also be an indication that that flare is malfunctioning or that it's been extinguished by mistake. So then it could be a sign for us to point the satellite to that region and start looking at whether or not there's methane emissions. And then finally, we also look at a predicting algorithm that tries to look at where leaks would be most likely to occur. So instead of just focusing on the most recent information, but in the past, we try to be forward-looking as well and try to predict where leaks will be most likely to occur based on all these trends and patterns that we see, but based on the flaring information, the hotspot information, the incident reports, the production levels historically, all these things, looking for these trends and patterns where leaks are most likely to occur. And then as we find more and more leaks, the algorithm learns and then gets trained to point us more effectively. And one last note here, this is useful for us to point our satellite to best serve the customers, but this information at that level is also useful for the customer as is, because now you can start making decisions on where you want to look at certain facilities based on risk prediction, based on what's happening with the flares, based on when you would expect the next measurement would be made. Would it be made with one of our aircraft? Would it be made with the satellite sensor? So you can start planning your day and planning where to look based on that information instead of taking a best guess as to where to look. So we're trying to provide these tools, and of course they can be molded to everyone's needs, but the overarching theme here is combining information to provide actionable insight. We want the information to be usable and useful. So I'll conclude here by just highlighting a few points that I hope you'll remember here and take away from this quick webinar. First, when you're looking at using satellite data to look at methane emissions, always make sure to question what's the resolution and what's the detection threshold, because those are key for attributing emissions to sites, but to do it reliably, consistently, and also in an operationally significant way. So that's very, very important. Now, I've shown that the next generation of our satellites at GHGSat is already delivering unparalleled performance and starts to unlock the possibility to really start working with different other technologies to fully close the loop on methane emissions. And finally, analytics has the power and the ability to augment the unique data that we generate with our satellites and make it actionable. So instead of just throwing data over the fence, we're very, very keen to make sure that that data can be used to make decisions operationally. What do I need to do with this? How do I act on it? Can I wait? Do I need to act right now? So these are all crucial questions that that need to be answered instead of just throwing data over the fence. So with this, I'll stop here, and I look forward to your questions.
Now, first, thank you very, very much for just an amazing presentation. Of course, I'm super interested in this technology. I believe it's going to transform really the way all the companies in the U.S. view the world. They have been so compliance driven, and because of the threat of EPA violations, they spend billions and billions of dollars complying with a myriad of regulations. I believe in the future, hopefully, the focus will be on emissions and emission reductions rather than just compliance. But that leads to the question of how is GHGSat and other, how are you working with entities like the TCEQ or the EPA, where, as you pointed out right now, they go and look at every single valve, every single flange, sometimes 4 times a year. And as valve technology has gotten better, gasket technology is better, industrial bolting is better, the vast majority of those fugitive components leak at such a low rate that the gasoline emissions related to the technician monitoring them are greater than the emissions from the valves and flanges themselves, because those have gone down so much over time. Yet the TCEQ, and I'm not knocking TCEQ, it's just that it takes time for regulations to change. This satellite technology that's coming out a year from now should completely transform the way we're doing fugitive monitoring, and that data comes in every day. Then drones could go look at the sources, take video clips of the exact valve or flange or thief hatch that's leaking, and then those resources go towards fixing leaks every day, not monitoring 10,000 valves over the quarter and only finding a valve leak at the end of that quarter that's been leaking for 90 days. Rather, every day, resources are put towards the actual source of emissions. So, with all of that said, my question to you is, are you working with agencies to get those agencies to be able or be ready to accommodate the regulatory change?
So that's a really interesting question, Steve, and it's a multifaceted question to answer. So I'll try to be brief here so we can address more questions. But it's what we do is really, I always describe it as 2 branches. So on the left, you have the branch that looks at working with emitters directly. So emitters are commercially interested in understanding their emissions, addressing them regardless of regulation. So sometimes it's motivated by regulations, that's great, but emitters are showing an increasingly a growing need and desire to understand emissions so they can be addressed. Now on the right side, the other branch is the regulatory aspect, the regulators, the EPA, the different governments around the world, and our system is obviously very useful for this. It is, however, something that takes longer to develop. It needs a lot more validation of the technology, a lot more testing to show exactly what to expect. And that's not something we could do very effectively with our first satellite, but now with the second one, this is something that we're doing more and more of these controlled release tests, really to get us on the radar of these regulatory bodies, which we all speak to. Some of them we already work with, For example, the Alberta Energy Regulator in Canada is you know, an example with whom we've already done some work. Environment Canada, we talk to the EPA quite often, and different people within the EPA. But the interesting quirk in all of this is that we can't apply to be approved as a means of reporting. It has to come from industry. So industry has to say, listen, you're asking us to look at all of our facilities with optical gas imaging camera 4 times a year. It's costly, it's inefficient, and frankly, like, it puts our people on the road way too much, and it's dangerous. So we've been trying this other technology, whether it's, you know, GHGSat satellites or drones from another company or whatever else. Can you please look at, you know, certifying those technologies for reporting? And then the process starts. It almost has to be sponsored by industry in order to truly you know, start and take shape. So a lot of the work that we're doing right now is with that in mind. We even have a project, a 2-year-long project right now in the BC, British Columbia, Montney region, where we're aiming to demonstrate 2 years working with 7 operators that are tiered system using analytics, satellite, and aircraft, and then once a year OGI is more efficient and cheaper than 3 times a year OGI across all of those facilities. So that's, you know, that's an example of a project that's in place to do that, to go towards this utilization under regulations of these new technologies. Your thumb might be on your
yeah, it is
again.
I'm so sorry. Yeah, there's satellite data, so lots of satellite data. Which satellite, I guess first, is your data publicly available, or is it only on a subscription basis? How does someone get the data that you are obtaining?
So we're a commercial company, so we sell our data. It's a subscription model. So operators or whatever partner we work with, it could be consultants as well that work in the industry. But they provide us with the coordinates of the sites that are of interest, and we start monitoring them on a regular basis. And then, depending on the level of analysis that's required, we start providing some of that information. So it is definitely for purchase. Now, there is data that's available publicly as well, but it's not necessarily available. It's not useful at the facility level. But again, through some of our services, for example, our analytics services, that we incorporate those in there as well. So it provides a kind of a full picture using all these instruments.
The floor.
Are you able to stay up? Are you able to see the chat? There was a few other questions on the chat.
Yeah, so I can start addressing the questions in order there. So there's a question from Kashif Malik asking, can this technology be used to determine the background concentration of methane that can be used for modeling analysis? And that's a really important factor, a really important thing to understand, is that there are other satellites that do this. Our satellite is not designed for this. Our satellite is specifically designed to look at sources. So a satellite like Tropomi, for example, looks at what's called absolute column concentration. So it's very good at looking at the background concentration over an area, over a region, over a country. For us, we're looking at specific sources. So in the absence of a source, we're not very efficient at looking at the background concentration, because our system is a differential system. So we measure the source, and then we get an approximation of the background. Then we subtract the background from the image. So all the methane that's above and across that source that's in the background, we subtract. And what you're left with, what we call enhancement over background, you get a really good approximation of the source only. And that feeds into the question from Thomas Didek here. Have you used a satellite to look at methane emissions from wetlands and agricultural sources, and then comparing them to those of industrial emissions? So agriculture is an area where we could do that. For example, agricultural feedlots. When you put 10 or 20,000 heads of cattle in a field, then you can start seeing enough methane for us to be able to detect. Now, wetlands. Now, and it's the same as we often get asked about melting permafrost, for example, because there's a lot of news stories about melting permafrost. The climate ticking time bomb, like the world is ending, and all of this. So, we have to take all of this with a grain of salt. Of course, it is a high quantity of methane, but the challenge here is that the whole background gets elevated. There's no single source. There's no single point where it's higher. So again, it becomes tougher for us to start evaluating this. But other instruments like Tropomi would be very, much better, much more effective at looking at that. Another question here from Brandt Ross. Regarding the measurements of coal mines, do you typically find emission at closed or reclaimed coal mines, or typically ones that are still in production? So we've seen it from both, actually, and so far we've had a lot more results at underground coal mines. And usually they are active coal mines because they have to vent the coal mine methane to protect the miners from explosions. But we have had the opportunity to measure some abandoned coal mines as well that are still venting quite a bit. And now with this new satellite, we're optimistic that some large open pit coal mines with like large piles that are accumulated on site, we might be able to measure that as well. So we plan to do several tests in the new year as well regarding that. Another question from Kashif asking, can you predict leaks at a manufacturing plant with multiple sources? Well, a good example of that is what we do in the Permian and in shale regions in general. So you have thousands of sources there, and we aim to try to predict where, which sites would be most likely to leak based on the factors that I highlighted. Now, we wouldn't necessarily be able to identify which part of a facility might be more likely. We would be more looking at the aggregate, like facility level, but that's already quite a leap from trying to look at these things blindly, trying to point the satellite in a blind way. So that's what we're currently focusing on. There's another question from Ed Kazemi, asking, do you foresee having the capability to be able to detect other emission sources such as NOx, SOx, or carbon dioxide? So the short answer is yes. I mean, it is part of our mission statement to look at other gases. The sensor is entirely tunable to other gases. We just have to tune it on the ground before it's launched. So right now, we've made a very clear decision to focus on one gas at a time. It was a lesson learned from the first satellite. The first one was designed to look at methane and CO2 together, and very quickly we focused only on methane. The lesson learned, part of that lesson learned was that we can get better results by focusing on a single gas at a time. So we're turning our attention back to CO2 now with a dedicated satellite payload for CO2 in the next year or so. And then as the business cases would come, we could look at SOx or NOx or any other air quality gas, as long as there's a business case. Again, we're a commercial company, so if there's an interest, for example, measuring emissions from ships is something that constantly comes up in the face of new regulations, and we've looked at that. If there's a business case, there's something we could do. I think we're almost against the hour here. There's one more question One more question here from Ed. Given that the satellite can point the location where the leak is happening, but not the actual source, like the valve or the tank, is there a list of compatible recommended devices that can be used in conjunction with the satellite to fully optimize the leak detection process? Very, again, thanks, Ed. Very good question, very clear. The state of the gold standard right now, as you know, for the oil and gas industry is the optical gas imaging camera. It's a very powerful tool on the ground. It's almost unequaled when you think about it. And you could put that camera on a drone, but now with the line of sight requirements, meaning that the pilot of the drone constantly needs to be able to see the drone, it ends up being quite limiting. You might as well send someone with an OGI camera in hand instead to do this. But the OGI camera can really help pinpoint. The weakness of the OGI camera is it can't really measure very effectively. So there's methods now to do quantitative OGI, but it's still, again, it would be time consuming and very costly to do widely. But once a site is identified as having a leak, if you deploy an optical gas imaging camera, you can find that leak very rapidly and then start the process to address it and fix it. So that's that's probably the gold standard right now. But there are others, different sniffer technologies, flame ionizing tools that can do that. And again, you can put any of those on drones. That could also be an application. So I think we'll end here, just 1 minute over. But thank you everyone for the great questions and for your attention. This was a great session. Thank you.
Yes, and I'll add to that last question, and thank you very much, Jean-Francois, for the presentation, amazing presentation. The webinar series that we have will go through nearly every single form of methane detection, from each of the different satellite companies down to the high altitude systems, through each of the drone manufacturers and the fixed wing applications. So we'll go through all of those. One interesting that ties really directly to what has been discussed today is Baker Hughes did get the BVLOS exemption, and that's what he was referring to as you have to keep the drone within line of sight. Beyond the visual line of sight is what BVLOS stands for. Baker Hughes got a BVLOS exemption for an entire county. And so industrial companies in that county, Loving County, worked with a combination of GHGSat and Baker Hughes Avitas. You could have that, daily look in that county, and then those drones can go, that because they have a BVLOS exemption, they can go to exactly that UTM coordinate, get a video image of the exact source, and create a maintenance record for that to be maintenance to be performed. Then once maintenance is performed, the drone can go back out there, see that the fix worked, and there's no longer a leak. So that's sort of the future. Right now, that's only available in one county and through one commercial provider, which is Baker Hughes. I believe in the future, say 5 years from now, as those BVLOS exemptions get relaxed, I think it costs a lot of money to get that BVLOS exemption. BVLOS exemptions will become more commonplace as they work through that. There are some changes, regulatory changes on the FAA side to make BVLOS exemptions a little less cumbersome. And as the drone technology improves, I believe that's what the world will look like 5 years from now. Every day, these satellites find leaks. Drones are go get video images of the leak, create maintenance records. Maintenance comes and performs the fix. The drone goes back out and checks it and confirms that on the maintenance record. And that happens over and over, and leaks are fixed every day, and we're only looking at leaks, not looking over and over at components that aren't leaking. But yes, all of the different technologies will be discussed in subsequent webinars, and those technologies, I believe, will start to become part of a tiered process. The big question is, how can the regulations address that? We've had optical gas imaging around for over 20 years, and it's just now in the oil and gas side, not really meaningfully in the refining or chemical side. So I think the big question here is, how do we get the regulations to change fast enough to really take advantage of this efficiency? This is all about, the greenhouse gas and climate change. And right now we have an extremely inefficient process of fixing leaks, of checking, 995 non-leaking components for every 5 that are leaking. And checking those 995, you're creating more emissions than you're reducing by finding the 5 leaks. So how do we get that regulation to change in less than a 20-year time frame? But very interesting, great presentation. Thank you very much, JF, and we look forward to seeing you all at the upcoming webinars.
That's great. Thank you so much, Steve. Thank you, everyone, and hopefully we can all get together in person for the conference in February. If not, I'm assuming that will go online as well, right?
Well, we're going to end up pushing it back. Right now, we've pushed it back to April. We may push it back to July based off of the vaccine rollout. The hotel's working with us, realizing that industry travel bans have to be lifted before we can do our in-person conference.
Right.
So that right now we've pushed it back to April 7th, 8th, and 9th.
Okay.
And we're working with the hotel to possibly push that back to July, August. And really, it's up to industry. As long as there's industry travel bans, we can't do the conference, because this is all about connecting and collaborating between industry, public-private partnerships, and regulatory agencies. So we will do the conference in person, and we'll just monitor the rollout of the vaccines, and we should have a couple of month lead time. Right. The last article I read, it looked like 70% of the population would be vaccinated by May. But travel bans tend to go by quarter. So travel bans probably won't be lifted for the first quarter, maybe not for the second quarter. That's why we're pushing for either April or July to catch the back ends of those travel bans.
Well, it's great that there's an end in sight anyway, and it's always better to do these events live anyway, so that we can all interact and speak to each other in person. So I look forward to it.
Yep, and thank you very much for the presentation again today. Thank you to all of the participants. And with that, we'll conclude today's webinar. Look forward to seeing you all at the conference.